A power transformer, an essential part of the electrical grid, helps transfer electricity over long distances. Inside, the core and windings work together to step up or step down voltage as needed. Here's the on-load tap changer, OLTC. It automatically adjusts the transformer's tap position to regulate voltage.
The oil tank of a power transformer stores insulating oil for cooling and insulation. The magnetic oil gauge monitors the oil level, ensuring it stays within safe limits. A drop in oil level can indicate potential issues like leaks or overheating, helping prevent transformer damage.
A well-designed core improves transformer efficiency and minimizes heat generation, ensuring reliable performance. The magnetic core of a power transformer is made of thin laminated steel sheets, designed to reduce energy losses due to eddy currents. It provides a low-reluctance path for the magnetic flux, allowing efficient transfer of energy between the primary and secondary windings. The primary winding is carefully wrapped around the magnetic core, in a circular shape. These windings are typically color-coded for easy identification: red, yellow, and blue for three-phase systems. The primary winding receives voltage through the input voltage terminals, which are connected to a three-phase power supply. A three-phase voltage system consists of three alternating voltage waves. Typically represented by different colors: red, yellow, and blue. Each of these voltage waves is 120 degrees out of phase with the others. This phase shift creates a continuous flow of power. In a three-phase system, the current flows through the windings in sequence, maintaining a 120-degree phase difference, ensuring a continuous and balanced magnetic field around the core. When voltage is applied to the primary winding, an alternating current flows through it, creating a magnetic field around the core. This magnetic field, known as magnetic flux, oscillates as the current alternates. Each phase offset by 120 degrees, producing a rotating magnetic field in the core. As this flux passes through the core, it cuts across the secondary windings, inducing voltage through electromagnetic induction and efficiently transferring energy. To learn more about how electromagnets work, check out the video pinned in the top right corner. Voltage in a power grid is not constant. It shifts with demand, supply, or network changes. To maintain a constant and stable voltage in transformers, tap positions are used. A tap changer modifies the number of turns in the transformer's winding, adjusting the voltage as needed. The tap positions in a transformer are connected to the secondary winding through different points along the winding. By changing these points, the voltage output is adjusted. In on-load tap changer, this happens automatically to maintain a steady voltage. Let me tell you about an on-load tap changer. It's a clever device that keeps the voltage steady in a transformer while it's running. How does it do that? Well, it adjusts the number of winding turns to control the voltage, all without ever switching off the power. Let's talk about the resistor type on-load tap changer. It's a handy device that uses resistors to limit the current during tap changes. That way, it keeps the voltage stable in a transformer without any fuss, all while the power stays on.
This is the motor drive in the on-load tap changer, a powerful electric motor designed to adjust transformer taps under load. Normally it runs automatically, but here, a manual lever is inserted into the drive mechanism, a sturdy steel rod connecting to the gearbox for hands-on control. As the lever is rotated, it engages the motor's shaft and gears, turning the tap changer step by step to shift the transformer's winding connections. This fine-tunes the voltage output without interrupting power. The OLTC consists of a moving arm, which swings left and right like a pendulum to make contact with different tap positions. This movement allows the transformer to adjust the voltage under load without interruption. Transition process. During the tap change, as the arm moves from one tap to another, it passes through a center position where the current flows through a transition resistor. This transition resistor helps to limit the circulating current, prevent arcing, and ensure a smooth and reliable transition between taps. When the voltage on the load side is higher than the desired value, the tap changer moves the arm toward a higher tap number on the winding. Higher tap number equals lower turns in the secondary winding, lower turns equals lower voltage output. As the tap is changed, the transformer effectively reduces the number of active turns on the secondary side, which steps down the voltage to the desired level. The primary function of the OLTC is to regulate the output voltage by changing the tap positions on the transformer winding. When the voltage on the load side is lower than the desired value, the tap changer moves the arm toward a lower tap number on the winding. Lower tap number equals higher turns in the secondary winding, more turns equals higher voltage output. By increasing the number of active turns on the secondary winding, the transformer effectively steps up the voltage to meet the required level.
In a transformer, oil plays a crucial role in performance and safety. Transformer oil, also called insulating oil, is filled inside the tank. It serves two main purposes. First, it acts as an insulator, stopping electrical discharges between internal components. Second, it works as a coolant, absorbing heat from operation and dissipating it, to prevent overheating. The magnetic oil gauge, or MOG, in a power transformer monitors the oil level inside the tank using a float mechanism. As the oil level changes, the float moves up or down, causing a magnetic coupling to rotate the indicator needle on the dial gauge. This movement provides real-time oil level readings, and triggers an alarm if the level drops critically, ensuring safe and efficient transformer operation. Reserving oil in the transformer tank matters, with the conservator keeping it full as heat changes. Then there's the breather. It stops moisture from getting into the transformer oil. As the transformer cools, air flows through the breather, where silica gel grabs the moisture, letting only dry air into the system. This keeps the oil and insulation safe from damage. The power transformer's cooling fans have stopped. Now, the cooling panel starts to heat up as the temperature rises. Then, the fans kick back on, spinning fast, and the cooling panel begins to cool down again. Back to normal, just like that.